Great. Yesterday we started talking about complex zeros, being able to find roots with respect to complex zeros. The only thing that's changed from what we did last week with respect to synthetic substitution and rational root theorem is now your solutions will come down to actual imaginary rational roots. Okay, so you can go through the exact same process before as you did before, but then you can sit there and go, okay, now how can I deal with this as a rational root? And as we talked about yesterday, there's different ways. There is different ways. And we went through a way of being able to find an irrational root yesterday. If you looked at the homework and you looked at solutions, there's also a second way that I have in there in regards to finding rational roots. Okay, so that's up to you. Whatever works for you works for me. It's fine, but you have to figure out a way of being able to make it work for you. Once again, the irrationals, I would tend to, if you look at the back side, if you go to the back side there, and you're trying to find all your solutions, I would go through until you get to a trinomial, and then start working through the idea of working with the complex complex solutions by using your quadratic formulas or whatever. Right, so I would save that to the very end and not worry about running through your 3i or your 2i or your 4i. Wait till you get your trinomial at the very end. Like in number 5, you have x squared minus 6x plus 10, and then sit there and work and try to find your complex solutions. And the last one, you have x squared plus 9. Find your rational or complex solutions at that point. Okay, I would not force what we have to do in problem number 1 and 2. Problem number 1 and 2, you have to sit there and see, do you have a rational root here, or I'm sorry, do you have a root or not a root with an imaginary solution? Okay, so you have to force it through. On the back, like I said, keep it simple for you. Questions you have, things you need me to go over? Yeah.
Number 4.
Number 4, which one, the first or second one?
Oh, the first.
The first one?
Yeah.
Roots of 1/2, -5, plus or minus 2i. 2i, negative 2i?
Yeah.
All right, take a look at number 4. We have roots. X is equal to 1/2. We have x is equal to -5. And then we have x is equal to 2 plus i and 2 minus i. Okay, so we should be able to get our roots for the first one. For first 2, we have 2x minus 1. For the first one, it'll give us our 2x minus 1 will give us our x equals 1/2. So you can make it today. Honors with your presence. Appreciate it.
We had to move our cards.
I'm kidding. It's okay. Then we have x plus 5 in there. Okay, we have those two solutions. Now, yesterday we went through one way of finding a solution with the imaginaries there, or the complex. I threw a second way in there at you. I like what we did yesterday. This gives us 2 plus or minus I. So we have x is equal to 2 plus or minus I. Subtract your 2 over. So we have x minus 2 is equal to plus or minus I. And then square both sides. If we square the left-hand side, we have x squared minus 4x plus 4. If we square the right-hand side, we get a value of -1. The plus or minus will cancel out with the square. It makes us positive, gives us positive I squared. Positive I squared gives us -1. So then we can add 1. So we have x squared minus 4x plus 5 is equal to 0. And this would be your last factor, x squared plus or minus 4x plus 5. As our polynomial. My other way, if you look at the other way there, is a little bit more involved. Once again, one way is getting the proverbial mathematical cat. As I go through, I find easier ways or better ways. I like this way a little bit better. Other questions? Yeah?
Is that how the multiplicity of 2 since is 2 plus I and 2 minus I?
No, because this is one solution here, 2 plus I, that's one solution. 2 minus I is one solution. Now, if I said you had another 2 plus I in there, then that would give you that multiplicity of 2. Other questions? All righty. Today we're going to work with graphs of rational expressions. Graphs of rational. Important that we keep up with the material. This is the time of the year. We start venturing our world into a vacation mode a little bit because we have a little bit longer lengthy breaks. The material's still going to be there. You need to continue to work at it because if you don't, it will catch up to you very quickly. I know we are all involved in a lot of other different activities. But it's important that you discipline yourself to making sure that you take care of your educational needs. Thank you, everybody. If we take a look at a rational expression, when we talk about a rational function, a rational algebraic expression. When we talk about a rational algebraic expression, a rational expression is, you could say, a fraction. You have a numerator in terms of x, and then we have a denominator in terms of x. Now, it could be a constant on one or the other. But you have a numerator and you have a denominator. And we have dealt with the rational expressions already. But all that we've done with these rational expressions is we looked at the idea of the domain. If we take a look at the rational expression here, we have 5x over x minus 5. The domain is your usable x values. What are your values of x that you can use? Well, if I look at my domain, I have a rational expression, 5x over x minus 5. We wrote this in interval notation. And what we want to do is we want to classify and list all of our x values. Well, anybody remember what our domain would be in this one?
X is a number of negative infinity, infinity, x cannot equal 5.
It could be negative to positive infinity. That's all real numbers. But we said x cannot equal the value of 5. Because what we have to worry about here is in a fraction that if we got 0 on the bottom. And the only way to get 0 on the bottom is if x is equal to 5. X minus 5 equals 0, 1 makes it equal 0. But we exclude that value. We exclude that value. Well, in the second one here, what would be your domain in the second one? Check your answer with somebody around you. It's going to be the same idea as you have x is a member of positive, negative, infinity, but x cannot equal what? Okay, remember what x not equal?
Negative 4 and 1.
Negative 4 and 1. Where we can see what we can't equal value 0, but we can look at what makes us equal to 0. So we can factor this down to x plus 4, x minus 1. That will give us the next value, negative 4, and a value of positive 1. Okay, we have to watch our negative signs. In your calculator, first off, you need to make sure your window is set to something that would work for us. So if you go to Zoom and hit 6, okay, so you hit Zoom and hit 6, that's going to set our windows to where we want. All right, we can now go to our y equals. Okay, clear out the fraction in your y1 if you have something in there. And I want you to clickety-clack in there, quantity 5x on top, and quantity x minus 5 on the bottom. Make sure you quantify both of them. And what we want to be able to calculate is we want to be able to calculate these values of this function at 4.7, 4.9, 4.99, and 5.01. Well, how do we deal with that with our calculator? Is if you go to second, hit your second button, and above the trace, you have the word CALC, calc. This will allow us to do some calculations. So what you should see is you should see values, zeros, minimum, max, so on and so forth. We only want to worry about just the value. Okay, so we want to calculate the value of our function that we have. And the value of the function, we want to calculate it at, first number, 4.7. So it's asking us, what does x equal? Well, I want to type in 4.7 and hit enter. we get negative 78.33. Now, you don't have to go through that process over again because the next value we want is 4.9. So all you have to do is type in 4.9 and it's automatically going to get there. And hit enter. Then do 4.99 and then do 5.01. Get water, that's fine. So we do our values. Ian, what do we have? 4.7.
Negative 78 point figure repeating.
4.9.
Negative 245.
4.99.
Negative 2,495.
And 5.01. 001.
25,005.
25,000 what?
And just 5.
Okay. So if we take a look as we get closer to this value of 5, we can't, if we try to do 5, okay, type in 5. See what happens if you type in 5. We said we can't use it. What do you get? You get a domain error. Okay? You have an issue with that. So at the value 5, we have an issue. But as we get closer to 5, from this side of 5, we start getting really big towards the negative world. As we go in from 5 from the right-hand side, so if we look at a number line here, at the value of 5, as we come to here, we get really big in this direction. As we come in from this direction here, from over here, we get really big in the negative direction. For those that are juniors in here, do you have any sophomores? Sophomores? You'll eventually get into the calculus world next year. In the calculus world, what we'll talk about is the idea of limits. Okay, and this will ease or better define what we talked about with respect to a limit. Okay, those that are going into college next year and you go into Calc 1 in college next year, you will start talking about limits in your first chapter or in your second chapter, and you'll further define what happens here. We talked about this in trig class. The idea of an asymptote when we were graphing our secant, cosecant, tangent, cotangent values or problems or functions. When we were graphing them, we talked about the idea of an asymptote is a line that is approached by a graph but never crossed. A line that's approached by a graph but never crossed. We have a vertical asymptote, which means it's going straight up and down. Vertical asymptotes occur at the values of the domain that are excluded. The values of the domain that are excluded. This will give us a vertical asymptote. When you plugged in the value 5 into our graph, you got a domain error. And the domain errors, we had to exclude them. What occurs there is a vertical asymptote. So if we take a look at our first equation up here, our first rational expression, we have 5x over x minus 5. The value we had to exclude was x cannot equal 5. So we have a vertical asymptote because vertical lines are in the form x equals. we have a vertical asymptote that x equals 5. The values that we have to eliminate in the second one, -4 and 1. So we have vertical asymptotes is x equal -4, and x is equal to the value of 1. The values you have to exclude is whatever makes our denominator equal to 0. So the vertical asymptotes occur at the values of the domain that we have to exclude. Well, the values that we have to exclude are the values that make our denominator equal to 0. We could talk about the x-intercepts. These are the values of the function where the function crosses the x-axis. Value at which the graph of the function crosses the x-axis. The x-intercepts is where y is equal to 0. Where y is equal to 0. Well, with a rational expression, we have our numerator of x divided by our denominator of x. What makes a fraction equal to 0 is your numerator equal to x. So your x-intercepts occur where your numerator is equal to x. Your y-intercept are the values of the function that cross the y-axis. That's where x is equal to 0. We can put x, our value of 0 in for x, and we can find our y-intercepts. The last thing to discuss here are horizontal and oblique asymptotes. The horizontal asymptote are lines that approach horizontally. Okay, horizontally, side to side. If the degree of the numerator is equal to the degree of the denominator, if the two degrees are equal, the degree of the numerator is equal to the degree of the denominator. Once again, when you get into calculus, we will better define this. Right now, we'll just look at characteristics. When we get into calculus, we once again take a look at limits and the idea of infinite limits. But for this, we're okay. How do we calculate the horizontal asymptote? It's going to be y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Now, once again, you have to go back to the idea of what, and mathematically, we can always go back to this, go back to definition. What is your definition of your leading coefficient? It is the coefficient to the largest degreed term. Whatever the coefficient of the largest degreed term is, that's your leading coefficient.
Excuse the interruption. Please dismiss students going on the Career Center trip at this time. Students going on the Career Center trip dismissed at this time. Thank you.
Okay, the rest of the notes will be out in the classroom. And screencast, find it too, so if you want to listen in. If the degree of the denominator is greater than the degree of the numerator, then the horizontal asymptote will occur at y equals 0. It's going to be the x-axis. It will be your x-axis. if the degree of the denominator is less than the degree of the numerator, which means you can divide into it. If you just had x minus 2 on the bottom, and then you have x squared on the top, we can divide x into x squared. That's a divisible thing. So that's when the degree of the denominator is less than the degree of the numerator. There's no horizontal asymptote, but you have an oblique asymptote. You have no horizontal asymptote, but you'll have an oblique asymptote. Now, what do we mean by an oblique asymptote? It's a slanted asymptote that has slope and y-intercept. You have a slanted one. It's not horizontal, it's not vertical, it's slanted. That means you have a slope and you have a y-intercept. And it will occur at the quotient of the division of the rational expression without the remainder. The quotient of the division of the rational expression without the remainder. Once again, this goes back to the idea of an infinite limit. Your infinite limit, your remainder goes to 0, and your function will approach that line as you approach infinity and beyond. Oops. Sorry about that. All right, so if we take a look, the degree of the denominator is 1. The degree of the numerator is 2. So we will have an oblique asymptote. So we can take x and divide it into x squared plus 2x minus 1. X goes into x squared, x times. X goes into 2x plus 2 times. We have x squared. This subtracts down to 0. Drop your 2x down. X goes into 2x 2 times. So we have 2x. We subtract. We get 0 there. Bring down your 1. X doesn't go into 1. Our remainder is 1. So this is what we did in the previous chapter, or previous section. We eliminate the idea of the remainder. So we have an oblique asymptote at y equals x plus 2. Whatever your division is, minus your remainder, that line, or it could be a parabola. You'll be asymptotic to it. It could be numerous things. We'll just deal with lines here. We'll be at y equals x plus 2. This changes into a plus. We want to find the oblique asymptote. My degree of the denominator is less than the degree of the numerator. So we can use this technique here of long division, or we can use synthetic division. Synthetically, if I'm dividing by x plus 1, what goes in our little box? What goes in our little box if we have x negative 1? So I'm going to drop down my 2, multiply by negative 1, add down to give me negative 1, multiply by negative 1 to give me 1, add down, which is negative 2. The remainder we leave alone. So we would get an oblique at our solution here, which would be 2x minus 1. So it would be our oblique asymptote. Once again, using a lot of tools that we just did, adding into new concepts. Now, let's see here. Okay, if we take a look at the first one here. We have to determine x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, or oblique asymptotes, and get a graph down. Well, we'll at least look at the x-intercepts, y-intercepts, and start the graph here. I'm not going to get you this involved because it's going to add a little bit different ideas to it, but that is beyond us for right now. But we'll get this started. Okay, x-intercepts. X-intercepts occur where our numerator is equal to 0. So where is x squared minus 3x minus 4 equal to 0? So we can factor that down. So that should occur at x equals 4 and negative 1. Y-intercepts is where x is equal to 0. So I substituted my 0 for x and I solve for y. So all my x terms, they go away. So I have 0 minus 4, and 0 minus 4. So we should have y-intercepts. Brady, where's our y-intercepts at?
Negative. Negative. Oh. 1.
1. Negative 4 divided by negative 4, which is 1. Vertical asymptotes occur at where your denominator is equal to 0. Because the vertical asymptotes are going to occur at the values you would have to eliminate from your domain. Okay, so the values you have to eliminate from your domain are where the vertical asymptotes occur. So you have your denominator equal to 0. What makes your denominator equal to 0 here? What makes this equal to 0?
Two.
2, and also
Negative.
negative 2. So we have vertical asymptotes is x equals 2 and negative 2. Horizontal asymptotes. Okay, we take a look at our degrees. The degree of the numerator and the degree of the denominator. What's the degrees of both of them, Emberlyn? 2. So my degrees are equal. Degree equals 2, degree equals 2. So they're equal. So if they're equal, then we have a horizontal asymptote. If these two are equal, leading coefficient of the numerator divided by leading coefficient of the denominator. Well, my leading coefficient of my numerator is a value of 1. Leading coefficient of my denominator is a value of 1. So we have y is equal to 1. So if we look at our graph, first thing we want to place in is our asymptotes. Asymptotes are dashed lines. We have vertical asymptotes at 4. At the value of 4 and at the value of negative 1. I usually get my asymptotes in first. We have a horizontal asymptote of y equals 1. Yeah. We have an x-intercepts at those were our x-intercepts, weren't they?
Yeah, that's what I was thinking.
Asymptote should be at 2, negative 2. There we go. My bad. Looked at the wrong one. There we go, 2, negative 2. Our x-intercepts occur at 4 and negative 1. And our y-intercept occurs at a value of 1.
The y other one should be negative.
Which, this should be negative 1.
The other asymptote.
Oh, vertical asymptote at negative 1.
Or the horizontal one. Right?
Horizontal is at 1.
Oh, 1. Shoot.
Okay, once again, when we talk about the asymptotes, and I'm going to go into this a little bit more tomorrow, we'll stop there today and we'll finish up the next two problems for tomorrow. If you want to work on those next two problems on your notes, that's fine. Those are the things that we're going to go over tomorrow in class, and we'll explain this a little bit more with respect to why we crossed it there. Adios. Have a good day.